All right, so we're going to shoot for a review this Friday. Let's say at 6:30. I will get the room set up. I'm pretty sure it'll be the same room. Long 207, I guess. So I'm going to talk about orthogonal set. If I say two vectors are orthogonal, what does that mean? Yes, I like that. Perpendicular. What does it mean about their dot product? So if I have two vectors that are orthogonal, their dot product is 0, 0, 0. Yeah. So an orthogonal set is probably exactly what you think it is. Yeah. A set of vectors say D1, D2, Dm is orthogonal. When we say this is an orthogonal set of vectors, if the dot product of any two different ones is 0. So if you've got any pair of them that are not dotting the same thing itself, then you get 0 for the dot product. That means that all these vectors are sort of mutually perpendicular. Right? So for example, there's my favorite set of 4 vectors that are an orthogonal set. Notice the dot product of any two, it's pretty easy to see at 0. So these vectors all sit at they're all mutually perpendicular. Okay. Let me give you a set in R3 that's a little bit more exotic. I mean, this is kind of in certain sense the best orthogonal set. Here's another example, and I'm going to come back to this example a couple times when we do some computation. Notice to test orthogonality, or to test that this is an orthogonal set of vectors, you have to dot every possible pair. So you got to dot these two. So the 3 dot products 2. The dot product of these two, of course, is 1, 0, minus 1, so you get 0. The dot product here is 1 minus 2 is negative 1 plus 1 is 0. And finally, the dot product here again, 1 minus 1 is 0. So these 3 vectors, and this is more because these are like 3 that you could actually draw in 3 space. These 3 vectors sit mutually perpendicular. So this is what it means to be an orthogonal set. Here's the first kind of big theorem. Yeah. Here's an orthogonal set. Vectors in Rn, then the set is also linearly So we see now that orthogonality is kind of strong. Set. So in particular, what this means is, if this is an orthogonal set, so these are all mutually perpendicular, then it's the condition of linear independence is forced upon it, right? So in other words, this set right here is actually a basis for whatever it spans. Right? Let me ask you a question. Given this theorem, what can you tell me about the relationship between M, the number of vectors I have, and N, the size of Rn? Suppose U1 up to UM is an orthogonal set in Rn. What is the relationship between M and N? Good. M, if you believe this theorem, if this is an orthogonal set, this must be a linearly independent set. And the only way for it to be linearly independent, it must be the case that you have less vectors than the dimension of the space, less than or equal. Everybody okay? So, good observation. So let's prove this, and I'm going to prove this because this technique is going to come up today all the time. And that was like that. I forgot to say the important word here. So maybe I'll write it down. When I talk about what we're talking about sets, I will usually be assuming that none of the vectors are zero. Of course, this could be a whole bunch of zeros here, right? Because zeros are orthogonal there, right? But that would be silly for me to do that. So proof. So I want to show that these vectors are linearly independent. So suppose the zero vector is C1U1 plus C2U2 plus CIUI plus CM. I just put that CIUI in there to be dramatic. Now, to show that this is a linearly independent set, what conclusion do I have to come to about the C's? They must all be zero, right? That's what I need to glean out of this. So what I'm going to do is I'm going to dot this. UI. So UI dot 0 is UI dot C1U1 plus C2U2 plus CIUI plus CMU, which is, let me point out, this is 0. When you got the 0 vector with anything, 0. And this is C1, U1, UI U1 plus C2, UI dot U2 plus CI, UI dot UI, CM, UI dot UI. Now, since this is an orthogonal set, what happens to this? UI and U1, they're dot product is 0 because they're at right angles, right? UI dot U2, also 0. Everybody agree? And the pattern continues. In fact, what's the only survivor? When you dot it with itself, that's the only way that you possibly don't get 0. So what do I get here? I get 0. Everything drops out because all the dot products are 0 except this one. I get CI times UI dot UI. Right. And what's UI dot UI? Well, remember, any vector dotted with itself is greater than or equal to 0 and is 0 if and only if that vector is the 0 vector, right? Since UI is not the 0 vector, and of course another way to look at that is this is the length of UI squared. And if this equals 0, then CI. So what we've shown in this little computation, when we dot this equation with UI, is that CI is 0. Just repeat this for U, dot with U1, dot with U2, dot all the way up to dot with UN, and you get CI 0 until set is linearly. Okay. Any questions? So, for example, the first two examples I did is set right here. And this set right here. These are all linearly independent sets because they're orthogonal sets. Okay. Okay. Yes.
You said that if it's orthogonal, it has to be linearly independent. If it's linearly independent, does it have to be?
Absolutely not. Yeah. Yeah. So, for example, that's a good question. These two vectors are linearly independent, but they're not orthogonal. Right? So I can draw a picture of these. One of them is 1, 0, so it's right here, and the other one's 1, minus.
Okay.
And that actually, I'm glad you brought that up because linearly independence, that's a strong condition. Orthogonal is super strong. And oftentimes we want a basis of vectors that are orthogonal. Well, and the reason is, and you'll see the reason actually with the next few theorems, is what it's easy to compute actually with orthogonal sets what the coefficients are in the representation. And this is important in all kinds of things. You see this in differential equations, you see this in Fourier analysis, you see this in lots of things that you all do sort of scientifically in your career. So here's a definition that I hope doesn't astound you too much. Definition. Let W and Rn let's be a substitute. An orthogonal basis for W is, hold on to your hats, don't put my sleeve here. A basis of W that is an orthogonal set. So, an orthogonal basis, just a basis of an orthogonal set. So, for example, this basis here, this is an orthogonal basis. If you cut the last coordinate off and just look at the first three vectors, right? So this 1, 0, 0, 0, 1, 0, 0, 0, 1, that's an orthogonal basis for R3. But let me point out that it's pretty easy to see that those are orthogonal bases because they're linearly independent. That's easy to show. And also, it's pretty easy to show that everything's a linear combination. A typical element of R4 is A, B, C, D. Right? A times this, B times this, C times this. So, for another example. But this is an orthogonal basis. For let me justify that a little bit. Of course, let me also point out that E1, E2, and E3 is also an orthogonal basis for R3, the easy one. But so is this. How do I know this? Well, how many elements do I have there? How many vectors in my set? I've got 3. What's the dimension of R3 and 3? Do I remember that? And this is a linearly independent set because it's orthogonal. And what do you know if you have a set of 3 linearly independent vectors in R3? What must it be? Bases. So just by that, in fact, there's 3 of them and they're orthogonal, that guarantees that's basis for R3. Okay. Now, here is kind of, so if you have a linearly independent set in the vector space, then every element of that vector space can be written as a linear combination of those vectors. There we go. But determining how to do that linear combination is sometimes computationally a pain. For orthogonal set, for orthogonal bases, this process is much easier, and it's very systematic, very systematic. So let me give you this theorem, and I'll show it to you in action. And the proof of this is very similar to the proof of the first theorem that we did here. Suppose U1, U2 is an orthogonal basis. Oh, not orthogonal basis. So suppose this is a basis for W, which is some subspace of Rn. So these are all in vectors, in dimensional vectors. If Y is in W, well, what does it mean for the vector Y to be in W? It means it's a linear combination of spaces. C1, C2, C2. Then there is a simple way to tell exactly what constants you need to make this Y out of the U's. The I coordinate is Y dot UI dot UI dot UI. Or another way to think of this is y dot ui times the length of ui. Because that's what ui dot ui is. And this is very easy to understand. Let me show you why this is true. And why this is true is very similar to previous code. So suppose y is C1, U1, C2, U2, CI, UI, C3. Now, what we want to do is figure out what CI is. Trying to figure out the formula. So, what we do is we take UI and dot the crap out of it. So, Y dot UI. Now, what happens when you dot UI with every one of these vectors? All the way up to here, and all the way here, the dot product with U1 and UI, the dot product U2 UI, all of those dot products are zero except for UI dot UI, right? So there is a massive bloodbath of things falling off the planet here, and you get CI, UI dot UI. That's all that's left on the right side. Everybody agree? And from here, out, and let me point out that this is not zero. Just to be careful, because I know that this is a basis. So the zero vector never appears in the basis. Right? And so now you got to do solve. CI y dot UI over UI dot UI. This idea is going to come up a bit later too, something called projections. Okay, any questions? Now, check this out. This is what's so cool. Let's go back to this example here. Okay, I'm going to leave this up here. Start right here. Emily,
Yes.
make up a vector for me. 3 numbers. I don't.
3, 0,
3, 0. Okay. Okay. So what I want to do is I want to express this in terms of this basis here, right? I want to use my theorem here, right? Well, I know that y is equal to C1 times the vector 1 minus 1, 1, plus C2 times the vector 1, 0 minus 1, plus C3 times the vector 1, 2, 1. Yes, and I'm going to call this U1, U2, and U. So I don't have to write this thing down all the time. Now, this formula says, okay, so C1 is y dotted with U1 over U1 dotted with U1. Okay, so let's check that out. What is y dotted with U1? It should be 4. Everybody agree with that? And what is U1 dotted with U1? Well, basically, it's the square of every one of these things, so it should be 3. Huh, how about that? Okay. Yes. C2 is y dotted with U2 over U2 dot U2 Well, let's see, what happens when I dot y with U2? I get 3 minus 1, so I get 2. And U2 dotted with U2 is 2. And finally, C3 is y dotted with U3 over U3 dot U3. So y dotted with this is going to be 3, so it's going to be 4 again. And when I dot U3 with itself, I get 1 and 4 and 1, 6. And let's taste this. I mean, I'm curious myself. So if I get, let's see, what was 4/3, 1 minus 1, 1, plus C2, 1, expected 1 of minus 1, and the last one is 2/3, 1, 1. This is, let's see, 4/3, 7/3, 2/3 is 9/3, which is 3. Middle minus 4/3, and plus 4/3 is 0. And the last entry is 4/3, minus 3/3 is 1/3, plus 2/3. So you know you've got something powerful, and just that formula just cranks it out for you. All you have to do is do a couple of dot products, and you've got to go. This is certainly better than setting up the system of equations, right? Because you'd have 3 variables and 3 unknowns, and you'd have to do some kind of row reduction. Okay. Any questions? Now, how many of you all are in Calc 3? I'm a little bit curious. Have you all done scalar projections, vector projections? Have you covered that? Well, it doesn't matter if you have or not. I think in some versions of Calc 3 you might do it, maybe some not. So we're going to talk here about projections. Okay, so I want to give you kind of the idea here. Suppose I have 2 vectors. Now I'm drawing this in a plane, but we're doing 2 vectors set in a plane here. Let's say this vector is U and this vector is Y. The first thing I want to talk about is something called a scalar projection. And think of this as the shadow. I'm going to call this S for shadow or scalar projection. This is called a scalar projection. Now, there are a couple of things to worry about. I mean, my picture oversimplifies things a little bit. Because you might ask yourself, well, what if U is too short for the shadow? That's still okay because it's along the path of U. Even if the U only came to here, the shadow would still be this length, even though it outextends U. Now, let me point out that the shadow can also be on the negative part. So, for example, if the picture were like this, then the shadow actually casts over here, but that's on the negative side, right? So what the scalar projection here is the length of the, I shouldn't say length, it's the number you get, and basically it reflects, its absolute value is the length of the shadow projected either positive or negative. By the way, this picture right here, I will get a positive scalar projection. For this picture right here, I will get a negative. It signifies the fact that's going wrong. Everybody okay with that? Now, actually, if you remember back to the days of your trigonometry, you can figure out exactly what the scalar projection is. let's call that theta, right, the angle between the two vectors, which we know from last time had q. And notice that S is actually, from this simpler picture, the length of y times cosine theta. Everybody agree with that? So that's just a small question. Trigonometry, the scale projection is that. And I also know something else from last time, and that is when I take y and I dot it with u, this is the length of y times the length of u times cosine theta, right? Everybody okay? So scale projection, notice this piece right here. That length of y times cosine theta piece is a scalar projection. Which equals y dot u over the length. This is a scalar projection. Notice, as predicted, you might ask yourself this: what happens here? The denominator there, the length of u, is always positive, correct? As long as u is a non-zero vector. I'm assuming u is non-zero. Notice y dot u is going to be, well, it's going to be positive if theta is, well, it's going to be non-negative if theta is between 0 and power 2. And if the angle is bigger, then you'll get that negative projection and you'll get a negative. So the scalar projection would be either negative or positive. The vector projection or the projection, the book called projection doesn't make a distinction. Vector projection y on u is written this way. They get like a little chapeau. And this is projection of y upon u. You look for some strange reason use this word where the letter L here to signify the subspace generated, subspace spanned by u. What is this vector projection? Well, let me try to make sure here. So what this is y. So it is a vector in the same direction as u on the length of the scale projection. That's kind of a big picture of it. So y hat. This is equal to, and I want to sort through this formula a little bit once you feel a little careful with this. This is y dot u over u dot u. Now, let me kind of take this apart for you. This is, as promised, this is in, this is a vector of, it's got some length of scale projection. It's in the direction of u. So And it could, again, could be plus or minus. Let me take this apart. Another way to write this is y dot u over the length of u squared. Remember, this part is a number divided by a number times a vector. So the scalar projection here is number divided by number. It's just a number. This is a number divided by a number times a vector. So this is actually a vector. Notice that this looks very similar. So another way that you can write this is y dot q over the length of u. So here's another way to write this. Notice this number here is the scalar projection, being positive or negative. And what can you say about this vector right here? U divided by one. Very good. This is a unit vector in the direction of u, right? And so what do? You take the unit vector in the direction of u, and then you magnify it and make it the length, the same length as the scalar projection. And of course, the scalar projection is negative. Same direction as you, sort of the opposite. Okay. Good questions thus far. So here's kind of a visual of what's happening here. Suppose I have, let's just do this as a fun. So let's suppose that I have an orthonormal, I'm sorry, an orthogonal basis. And suppose I have some other vector. And this is one of the uses of scalar or the vector projection. Yeah, the vector projection. And if you've ever had a physics class, then you would probably, or a statics class or dynamics class, then what you want to do is you want to take this vector and resolve it in terms of this orthogonal basis. And why is this projection stuff important? Well, the way to do this is take the shadow on the V, on your basis elements here, and then take the shadow on the U. And now notice that you have these vectors here. This is a scalar multiple of U, and this is a scalar multiple of V. And now you express Y as multiple of V, multiple of U. And what those scalars are have to do with the scalar projection. So basically, Y is a spectral projection here plus a spectral projection. And many of you have known one of the important things to do in like physics and body diagrams and statics and dynamics is you break these things up into components to solve free body diagrams. Any questions? Okay. Now, I used this word accidentally a couple of times, and now I'm going to tell you what it is. Definition. The set of vectors S equals U1, U2, U n is orthonormal you might want to venture a guess what we think was normal. It's sort of like orthogonal on steroids. It's an orthogonal set, so it's just everything's got to be mutually perpendicular. And here's the normal part. Each UI is a unit vector. Now, let me point out that any orthogonal set can be turned into an orthonormal set. How can you do that? So let's go back to the well again. Notice, let me point out that in Rn, the set of vectors E1, E2, all the way up to En, that's orthonormal because they're orthogonal and the length of each vector of each of those vectors is 1. This is orthogonal, right? But it's not orthonormal. How can I fix it and make it orthonormal? Yeah. That's right. All I gotta do is tweak this a little bit, make it an orthonormal set. The magnitude of this, let's see, when you got it with itself, you get 3, so the magnitude square root of 3. The magnitude of this is the square root of 2. And the magnitude of this last one, see, 1, 4 is the square root of 6. This is how an orthonormal set. So given any orthogonal set, you can get an orthonormal set. Orthonormal sets are a little bit more convenient. I mean, the real convenience is orthogonal. Orthonormal is a little bit more convenient because it lets some of the formulas collapse to something a little bit similar. So for example, remember this formula here. Remember that formula we had earlier, figuring out the coefficients of the linear expansion test. If the set is orthonormal, what's that denominator going to be? That is correct. Remember, this is y dot ui over the length of ui squared. And if it's orthonormal, then you get much easier form. But it's a little bit more convenient. Okay. Now, let me throw in, I'm gonna do a couple of quick theorems about, so we've got these orthonormal sets, we've got orthogonal sets with normal sets. What happens if you fill up a matrix with columns that aren't just linearly independent? What if you have columns that are orthogonal, columns even that are orthonormal? Right? So, here. If A is a matrix not necessarily square, but in by any matrix. Then A has orthonormal columns. If and only if A transpose times A. Let's see. It's what, anybody want to guess? The n by n identity. Because what happens is when you multiply sort of two different columns, you get zero, because the dot product is zero. And if you multiply a column by its transpose, its own transpose, you get one. I want you to think about why that's true. See if you can do a computation and convince yourself that it's not terribly difficult. And I think it's good to kind of do the exercise, see what it's about. If you have 21 columns and X vector and Y vector are then then number one, if you look at magnitude of the length of your X vector, this is the length of X vector. So when you do the length, it doesn't change the length. Two, if you dot UX so this is if this is UX dot UI, this should be the same thing. X dot Y. And UX dot Y is equal to 0 if and only if X dot Y. And of course that follows. So in particular, what that means is the transformation X goes to UX preserves both length and orthogonality. Finally, I'm going to one last definition to point out. And this definition is rather, let me kind of point this out here. A square matrix could be the square matrix. We say U is orthogonal if U inverse is equal to U transpose. That is to say, U transpose U is equal to U. Now, let me point out something that's rather unfortunate about the terminology here. What it means for a matrix, a square matrix, this is fine for a square matrix. A square matrix is orthogonal, means that its inverse is its transpose. What this means is the columns of the matrix are orthonormal. So why don't we call it an orthonormal matrix? Well, some people in stats do actually, but the historic terminology is an orthogonal matrix, even though it only says orthogonal, it actually means the columns are in fact orthonormal. Let me point out, you might think about this, it turns out that if you have an orthogonal matrix, the columns are orthonormal and so are the rows. So see if you can figure out why that's possible. Okay, any questions? Any questions? All right, well, if not, anybody let me know if you've got problems Friday, but I'll get the room set up and I'll see you on Wednesday.